तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Continuing our discussion about differential amplifier, we saw in yesterday's lecture how VID is VBE1 minus VBE2 and IE1 minus IE1 plus IE2 is I naught at all times, and then we saw that IE1 by IE2 ratio is exponent VI by VT, from which we derived V naught as equal to minus I naught RC tan hyperbolic VI by 2 VT, I naught being equal to VE minus V gamma by RE. Then we said we will plot this, and this plot tells us that for VI negative, output is going to be positive, VI negative, right. This is going to be minus 1. And there is minus 1 here, so it is positive I naught RC. Vi large positive, this 1 will become negligible and this will go to 1. So, this actually switches between plus 1 and minus 1. This is the characteristic of hyperbolic tan function. And this goes from I naught RC to minus I naught RC, and that is the output swing of a differential amplifier. Now, let us see how this is equal to minus I naught RC, and if e to power x you expand it as when x is small, that means for VI by VT much less than 1, right. You can say that this is 1 plus x plus x squared by factorial 2 and so on, right. So, you can see that out of this, if you just put it as 1 plus x, ignore the higher order terms, then this is minus 1 and this is plus 2, because again compared to 2 Vi by Vt is negligible. So, even Vi by Vt is neglected there, whereas here this one gets cancelled with this one. So, Vi by Vt becomes dominant factor. So, you can't neglect it. So, this becomes is minus I naught RC into Vi divided by 2 Vt, which is nothing but, if you look at it, minus Gm into RC, because Gm is IEQ by Vt. IEQ is I naught by 2 for each transistor. So, Gm is equal to IEQ by Vt. This is I naught by 2 for this differential amplifier. So, we know that this is I naught by 2 Vt, that is Gm, this into RC. This is what we had earlier surmised from small signal equivalent. That means, small signal here means Vi is again much less than Vt. Okay. So, Vi is much less than Vt, same thing that we had used earlier for common emitter amplifier. So, now this defines what is meant by small signal in the case of differential amplifier. Now, what is a hyperbolic tan function really speaking? Right? Hyperbolic tan Vi by 2 Vt can also be expanded as what? Can you from this conclude what it is? Hyperbolic sine function by hyperbolic cos function, right? So, if that is the case, what is hyperbolic tan function strictly speaking? It is true that we will have minus I naught Rc into Vi by Vt as one term, first term, Vi by 2 Vt. Okay? So, Vi by 2 Vt means tan hyperbolic x is x, then what else? The next term is not square, but cubic, right? In the hyperbolic tan function, right, you will not have the square function coming into picture. Okay? Why? This is because they get cancelled with one another, right? These square functions, okay, Vi by Vt whole squared and Vi by Vt to the power 4, all these things, and then you get cubic and fifth order like that. It is an odd function. Right? So, you will see that as far as the differential amplifier is concerned, the nonlinearities will be less than the nonlinearities in common emitter amplifier, where you have what kind of nonlinearity? Exponential nonlinearity. That means e to power x is okay 1 plus x squared by 2 factorial, so on. So, all the terms are existing. Okay. So, after x you have x squared by factorial 2. Here after x you have x cubed by factorial 3. Okay. And therefore, obviously the extent of distortion here is much less than that in the common emitter configuration, and it will give the same small signal, gain, input impedance, etc., but distortion is less. Is that clear? Now, we will illustrate it later by an example. Okay. However, here we can see that tan hyperbolic nonlinearity, okay, results in only what kind of harmonics at the output? Only odd harmonics existing at the output if I apply a sine wave. Okay. Whereas, in the case of a common emitter amplifier, all harmonics are invariably present. That can be seen. How is it obvious for us here? Now, for if it is a fundamental that is applied, okay, you have, okay, for the fundamental a phase shift of, okay, 180 degrees here, right, and no phase shift between this and this. Okay. And for the let us say, since it is a function where the square law gets eliminated, okay, because of the difference. The how it happens is because of the difference, okay, there is no phase shift between the even functions, right, and they get cancelled with one another, okay, and only the odd functions remain. Now, that is illustrated very clearly by this hyperbolic tan nonlinearity. Now, this slope here, this is nothing but delta V naught by delta Vi is nothing but this, right. It's going to be, if you do that, please do the differentiation of this from using the hyperbolic tan function and show that delta V naught by delta Vi is nothing but the gain, okay, is the same as minus I naught RC by 2 Vt. It is the slope that we have illustrated here by making approximation, right. You can do that mathematically by finding delta V naught by delta Vi, delta V naught by delta Vi, okay, as minus I naught RC by 2 Vt from this. Now, the negative sign is also indicated by the negative slope here, and the slope will keep on decreasing. That means, if there is an offset in this differential amplifier, the gain is going to be less, small signal is going to be, the small signal gain is going to be less, and not only that, the swing also is going to be less. If there is an offset, if the operating point is not this, what is an offset? Even when VID is 0, okay, this voltage is not 0. Why is it going to happen? Simply because these two transistors are not so matched, okay. IE naught of this transistor is not same as IE naught of this transistor, in which case even when this is 0, okay, then these two currents will be what? Different, even though the base to emitter voltages are the same, okay. So, the output will be having an offset. Now, I would like you to understand something about the offset now. What is the offset? Offset, output offset is that voltage that appears when the input is 0. Output offset is that voltage that appears at the output when the input is 0. So, we have what is called output offset. Why does it happen that there is an offset? That is because the transistors may not be that is IE naught, okay. Transistor 1 T1 is having IE naught 1 and transistor T2 is having IE naught 2 as its reverse saturation current. Then what will be IE1? IE naught 1 exponent VBE 1 by VT. IE2 is equal to IE naught 2 exponent VBE 2 by VT. So, what will be the ratio of the currents when the input is 0? If VID is equal to 0, then VBE1 is equal to VBE2. Is this clear? If VID is 0, VBE1 is equal to VBE2. If this is shorted, this voltage is always same as this voltage, right. Then VBE1 is same as VBE2, therefore, IE1 by IE2 is not equal to 1. You take the ratio, it is IE naught 1 by IE naught 2. Is this clear? Is this understood or not? And IE1 minus IE2 by IE1 plus IE2 equals this ratio, okay, IE01, okay, minus IE02 by IE01 plus IE02. What is this? IE1 plus IE2? That is always equal to I0 and IE1 minus IE2 is equal to IC1 minus IC2 by alpha. IC1 minus IC2 by alpha. IC1 minus IC2 into RC is equal to minus V0, that we had already written earlier. IC1 minus IC2 into RC is equal to minus V0. And therefore, V0 now this offset, this is what is called the offset voltage, output offset voltage equal to minus alpha I0 RC into IE01 minus IE02 by IE01 plus IE02. So, if you know the extent of mismatch of IE0s, IE01 minus IE02 is the mismatch, okay, IE01 plus IE02, then you know the output offset as minus alpha I0 RC into this mismatch factor, right. So, this is an important aspect of output offset. So, if there is a mismatch, you can tell based on the extent of mismatch what the output offset is going to be, and our effort should be to make IE01 as close to IE02 as possible, so that this V0 offset is always close to 0. Okay. So, if it is close to 0, fine, we get the maximum gain, okay, which we intend to have, but otherwise the gain will keep decreasing depending upon the offset. Therefore, the offset itself is not a serious problem, it can be compensated. It is a constant voltage. If it is a constant voltage which does not vary with time, then it is not a problem. Unfortunately, it is a DC which drifts with time. This is what I have told you. So, it keeps changing with respect to time because of dependence of IE01 and IE02 with respect to temperature, and they may not track exactly, and therefore, this fact that these vary with respect to temperature causes the output voltage to drift with respect to time. So, even when the input signal is not there, it is indicating an output signal which is time dependent. Okay. This is adding to the noise. Okay. This itself is now generating some amount of noise. Okay. Particularly, this is of great nuisance in the case of low frequency amplifier, where the signal also changes very slowly with respect to time. We cannot separate out this from this signal. So, it interferes with the signal. Therefore, in a good amplifier, we must make this as close to 0 as possible. Not only that, then it should not further drift with respect to time. These are two important things. Now that we know the origin of this offset, it will be clear for us how to compensate for this offset also, so that if it is not 0, how to make it equal to 0. Now, therefore, input offset definition is, this is output offset. Is this clear? When the input is 0, what the output is, this is called output offset. Input offset we will now talk about. Input offset is that voltage that has to be applied to the input in order to make the output go to 0. input offset. These are all important parameters associated with the differential amplifier. Input offset is that voltage that we have to apply at the input in order to make output offset, output voltage, okay, go to 0. Is the definition clear? Now, how do we find out input offset? It's very clear. Input offset is that VID that I have to apply, so that exponent VID by VT, okay, this becomes equal to what? This becomes equal to, what is this normally? IE1 by IE2 equals IC1 by IC2. That is what we have put, right? In order to make the output offset 0, I have to have IE1 equal to IE2, IC1 equal to IC2. That means this should go to 1. So that means VID for that, okay, this should go to 1. So what is that? This is equal to, right, IE1 is IE0 1, okay, into exponent what? VBE1, okay, by VT, and this is IE0 2 exponent VBE2 by VT. Right? Is this clear? Strictly speaking, when IE0s were matched, this was going to what? 1. This was becoming equal to exponent VID by VT. Is this clear or not? This was equal to IE1 by IE2. IE1 was IE01 exponent VBE1 by VT. IE2 is equal to IE02 exponent VBE2 by VT. IE01 when it was equal to IE02, this was going to exponent VID by VT, and this should then become equal to 1. So in this case, if this is 1, okay, when IE01 is not equal to IE02, if IE01 is equal to IE02, then we will get exponent VID by VT equal to 1 or VID equal to 0. Okay? That is the input offset. If IE01 is not equal to IE02, then even when IE1 by IE2 is equal to 1, exponent VID by VT is equal to IE02 by IE01. Earlier it was equal to 1, and therefore VID was equal to 0. Now obviously VID is equal to the offset voltage. So this is equal to VT log IE01 by IE. So this is an important thing. Input offset is equal to VT log IE01 by IE02. So it may be positive or negative depending upon whether IE01 is greater than IE02 or IE01 is less than IE02. The order of this is typically about a few millivolts, say 1 to 2 millivolts typically, because this is about 25 millivolts, okay, and IE01 by IE02 is practically close to 1. That means log of 1 is pretty close to 0. IE02, okay. So the offset voltage is minus VT log, that only changes the sign. Okay. So, the sign can be positive or negative, that is of no consequence, right, depending upon whether IE naught 1 is greater than IE naught 2 or IE naught 1 is less than IE naught 2, because we have not said which is really the input offset, right. So, it can be plus minus, okay, VT log IE naught 1 by IE naught 2. So, typical value for BJT is, this input offset is 1 to 2 millivolts. Okay. Therefore, you must always know this, that a single stage circuit like this with one pair of transistors will result in something like an offset of 1 to 2 millivolts. If you put Darlington pair here, okay, Darlington pair means actually you connect a transistor like this, okay, and another transistor like this in order to artificially boost up the beta of the transistor. Now, there are two pairs coming into picture, the uncertainty will be double, right. So, it will be 2 to 4 millivolts. So, using more pairs of transistors will result in more input offset, okay. Even though you might put this in order to improve the beta of the transistor, you will degrade the transistor differential amplifier in terms of its input offset. So, the best for lowest input offset is a single pair, not these modifications. Never modify this, right. The best thing is just a single pair if you are interested in maintaining minimum offset. Such is the case with amplifiers, particularly usable for very low frequency, where this offset has to be kept at a low value in order to prevent the output from drifting. Okay. We have seen that the current ratio IE1 by IE2 is same as IC1 by IC2 is equal to exponent VID by VT if the two transistors are matched. Otherwise, of course, it is going to be IE naught 1 by IE naught 2 into exponent VID by VT, and from which we could get the input offset, etc. Now, let us discuss once again about how this VID can swing this current, okay. Portion of this current is going to flow through this. Initially, this will be I naught by 2, this will be I naught by 2, okay, when VID is 0, if the two transistors are matched. Now, let us apply VID. The current ratio is going to be varying according to this. If VID is 0, this will be 1, and IE1 is equal to IE2 equal to I naught by 2. Now, by therefore applying VID, I can make the current IE1 much greater than IE2. This current will keep on increasing, this current will keep on decreasing. Ultimately, what happens? This transistor will have the total current I naught, and this will have 0. That is the limit. Okay? This is off, T2 is off, T1 is fully drawing the current. At that point of time, this voltage is going to be VCC minus I naught RC. This will be VCC because there is no current here. So, therefore, this output voltage will be VCC minus I naught RC minus VCC, and therefore, it is minus I naught RC, right. When VID is a large positive, output voltage will go towards minus I naught RC. Then I make VID now negative, this current will increase, this current will decrease as determined by this ratio, right. And this will keep on increasing if I make it more and more negative, and ultimately T1 will go to off state and T2 will take the complete current, and this voltage will be VCC minus I naught RC, and this will be VCC, and V naught will be I naught RC. And this is called current switching. What has taken place now, by applying a VID of positive polarity and going to negative polarity as far as VID is concerned, the current here has totally switched from this transistor to this transistor. This is called current switching. And any logic circuit, okay, using this for driving the transistors off, this logic circuit is called current mode logic circuit. So, a differential amplifier is belonging to a family of logic circuits called current mode logic circuit, or it is in this particular case popularly called, okay, emitter coupled. Emitter is coupling this transistor, okay, it is coupled at the emitters to a common point. So, this is called emitter coupled logic, or popularly ECL, or current mode logic, ECL or CML, current mode logic. This by nature, because only the current is switched from this to this, okay, by nature is the fastest known logic family. Resulting in any computer designed using this logic family will be the fastest computer then, right, as far as transistors are concerned. So, any computer using such logic family is going to be the fastest, okay, logic family computer, and therefore fastest computer. Why is it fastest compared to other logic families? When the current is completely switched to this, the potential here is VCC minus I naught RC. At that point of time, T1 should not go to saturation. That means there should be enough collector to base potential, which is positive in this case, in order to retain T1 in active region. This is an important aspect. If when this current is completely switched over to this transistor goes to saturation, everything is lost. It has to come out of saturation before it can really respond to the input signal. That is causing a certain amount of delay. Okay. All your TTL, okay, circuits got into the problem of low speed only because they were going into saturation. Then came about what is called Schottky TTL, where VCB was forced to be retained close to 0, preventing such transistors from going to saturation. They were faster than the ordinary TTL. However, ECL by nature is the fastest without the requirement of introducing Schottky barrier, okay, junction diodes. Okay. So, between collector and base. So, this is the fastest logic family. Here we have the current switching taking place, and the logic level in this particular case is going from VCC, okay, if you consider one side, VCC to VCC minus I naught RC, on the other side also, okay, VCC minus I naught RC to VCC. Or if you take the differential, okay, it will go from I naught minus I naught RC to plus I naught RC. However, if you connect an identical differential amplifier as its output, okay, this is again connected, normally that is the state, okay, of most of the logic circuit. This logic circuit will be further connected to another logic circuit. So, the extent of voltage variation, okay, will get limited just like this happening at the input. Okay. At the input, we need only a change in voltage of the order of few tens of millivolts to switch the current from one transistor to other. Let us investigate this. How much voltage is needed at the input in order to switch the current totally from one transistor to other? This is an important aspect of finding out, okay, the drive requirement for such logic families. Okay. So, the question is, what is the VID required to take the current from one transistor to the other and vice versa? Now, if you see the relationship, it is exponential. That means, when VID is plus infinity, okay, and VID is equal to minus infinity, only this takes place. But in all such situations, we say that the current is completely switched over to this transistor when this transistor gets 90% of the total current and this transistor has 10% of the total current. Is it clear? This is always the case in making a measure of what kind of voltage you require for such drive. Okay. So, I want this transistor to get 90%, this transistor to get 10%, that will be one voltage. The other voltage will be when this is 10% and that is 90%. Let us therefore call VID1 as that voltage where exponent VID1 by Vt is equal to IE1 is 90% and IE2 is 10% of I naught. Okay. Is this clear? This is one. Then exponent VID2 by Vt corresponds to this 10 and this 90. And what do we need? We need VID1 minus VID2. Okay. What is the extent of variation in this, okay, which will cause this switching from one transistor to other and vice versa, right. So, you divide this one by other, you get exponent VID1 minus VID2 by Vt equal to, how much is it? This is 9 and this is 1 by 9. Dividing one by the other, we will get it as 81. Clear? And therefore, VID1 minus VID2 is equal to Vt log, natural log of 81. Okay. Vt, please remember, natural log of 81. So, that comes out to be how much? 114 millivolts. This is an important conclusion, right. The voltage swing that is required to switch the transistor from one to the other and vice versa is only about 114 volts, millivolts. Okay. Please remember this always, okay, and how it can be derived. So, in the case of emitter coupled logic, you will see that the logic level for 0 to logic level to 1 should only swing from one value to other by an extent of 114 millivolts. Okay. Unlike in the case of TTL etc., where the swing is about 5 volts. Okay. This is the kind of thing. Next problem. We will come back to our analog circuitry now. We would like to know what is meant by distortion. Okay. What should be the small signal? Okay. What is the quantitative measure of the small signal in order to maintain distortion at a certain level? This we did in the case of BJT common emitter configuration as well. What should be the magnitude of VID if it is a sinusoid that I should apply here in order to retain distortion at the output lower than a specific value. Okay. And this will also facilitate comparing this with that of common emitter amplifier. So, we have seen that this V naught is equal to I naught RC, that is minus tan hyperbolic VID by 2 VT. Now, we are taking VID as equal to, what is it? Vp sin omega t. I am applying a sine wave as the input. So, as far as the x factor is concerned, we know that this is straight away coming as VID by 2 VT. This tan hyperbolic VID by 2 VT can expand as this. If it is x, it is x minus x cubed by 3. That means VID by 2 VT minus x cubed VID by 2 VT whole cubed by 3 and so on. Right? The other factors are going to be ignored. So, if we now consider Vp sin omega t as VID, this will be Vp sin omega t, okay, this whole thing into I naught RC with a minus sign is the output. Right? If VID is Vp sin omega t, this is going to be minus Vp sin omega t divided by 2 Vt minus Vp sin omega t whole cubed, that is VID. This will be 8 Vt cubed, therefore, this will be 24 Vt cubed. This into I naught RC. Now, as far as the gain is concerned, you can see that I naught RC divided by 2 Vt. So, output will be corresponding to Vp sin omega t into I naught RC divided by 2 Vt with a minus sign. What does it indicate? This is the gain, this was the original signal, and there is an inversion, there is a phase inversion. This is nothing but, this whole thing is nothing but GM of the differential amplifier, GM into RC. Each transistor is operating at I naught by 2, and therefore, that I divided by Vt is the GM, that is GM into RC. So, this is GM into RC minus GM into RC into Vp sin omega t. This is actually the wanted input. This factor is going to cause certain amount of distortion in the signal, because apart from sin omega t component, we will have other components also coming into picture. So, this Vp sin omega t whole cube could be expanded as, that is equal to Vp cubed, okay, 3 sin omega t minus sin 3 omega t by 4, that is sin cubed omega t. Okay. So, that divided by 24 Vt cubed, okay, is what is going to remain of this, right. So, this factor therefore is going to contribute to certain amount of distortion because of the third harmonic. Okay. So, the third harmonic distortion is going to arise here. Now, let us compare it with the fundamental. The fundamental component was Vp by 2 Vt, peak value Vp by 2 Vt. This is the fundamental component. As against that, we have this, which is going to be the amplitude of the harmonic, which is going to be, let us say, Vp cubed by 96 Vt cubed. Okay. So, we have this equal to Vp squared by Vt squared, okay, into 48, correct. So, this is the ratio of the third harmonic to the fundamental. This is also going to be the ratio of the percentage distortion. If you multiply it by 100, this will give you the percentage distortion. So, this will give you an idea as to how to control the percentage distortion in your differential amplifier. This, if it has to be 1%, then this factor should be less than 0.01. Now, that is how you have to control the differential signal amplitude. Okay. Now, we have another aspect of the amplifier to be taken care of in the differential amplifier. If this is operating at a current of I naught, apart from the differential signal, you have a common mode signal which is coming into picture, Vc I. So, if there is no differential signal, only common mode signal is present, how do we now fix up the sort of signal limitation at the input? If this is Rc, this is also Rc, this is Vcc, then the current in this will be I naught by 2, I naught by 2. And since the common mode signal is not going to cause any change in this current, so this common mode signal, when it is increasing, the reverse bias voltage applied to the transistor will keep decreasing. So, this can go on up to Vcc minus I naught by 2 Rc. Right. This voltage is going to remain almost constant at Vcc minus I naught by 2 Rc. So, this cannot rise above that, particularly if such an amplifier is the input stage of an op amp or something like that. If the common mode voltage changes above this, this transistor will lose its active nature and it will come to saturation, and the polarity is going to change from negative, that is feedback is going to change from negative to positive, and that will cause what is called as this instability, right, signal dependent instability. Right. So, this kind of thing can be prevented if you take care to see that this common mode voltage does not exceed this. Here on the other side, this voltage can go down and this voltage will follow this, Vc minus V gamma will be the voltage here, and at that time this current source should remain still active. So, that is the condition. So, there is a limit on Vc max as well as Vc minimum as far as the input stage is concerned.